So this last section of chapter 3 is about permutations and combinations, and I'm going to focus more of the counting aspect of this. We'll do a little bit of probability problems at the end here, but I mostly want to just focus on the counting aspect of this, and I think it's important to understand what permutations or combinations are. Combinations are especially important for what we're going to be doing at the beginning of chapter 4 next week. So that's going to be key there. So first of all, for permutations and combinations, a permutation is basically an ordered arrangement of objects, and the number of different permutations of n distinct objects is denoted by n factorial. So that's not an exclamation point, and it looks like an exclamation point, but in math we call that a factorial. You may or may not have seen this before. So for example, if I want to find out how many ways I can rearrange 3 objects, 3 factorial is 3 times 2 times 1. So we take the number and we multiply by all of the integers that come before it down to 1, which is 6. So 3 factorial is 6. 5 factorial is 5 times 4 times 3 times 2 times 1. So this is going to be 120. Actually, I'll just write it on my line here. So there's 120 ways you can rearrange 5 objects. 0 factorial is a special case. 0 factorial is actually equal to 1, and that's because if you have no objects, there's still one way to rearrange them, which is kind of weird, but that's really how it is. So 0 factorial is not equal to 0, it's equal to 1. 6 factorial is equal to 720. Now when you get to larger factorials like this, it's a pain in your calculator to put in 6 times 5 times 4 times 3 times 2 times 1 and so on. But on your calculator, on your scientific calculator, there should be a PRB button. So press the PRB button, and I'll try to find a video to post for you to teach you how to use combinations and permutations, or you can just look it up because everybody has a different calculator. So I probably won't post a separate video now that I think about it, because just everyone has a different calculator. But there's a PRB button, and you should find the factorial button. And if you just type in the number, press that factorial, or by scrolling over right or left or up or down, so you may have to do that, but it should do it for you. Now factorials grow at an extremely fast pace, which is kind of interesting. So if you type in 70 factorial, most scientific calculators cannot handle it. You'll get something called an overflow error. And overflow error, and that just means that there's basically more than 100 digits, which is huge, right? 100 digits is so big. That's larger than the number of atoms in the universe. 70 factorial is larger than the number of atoms in the universe, which is like mind-boggling, right? I mean, that is a huge, huge number. So that's just a kind of a fun fact about factorials. They grow faster. A factorial function will grow faster than an exponential function will. So in Algebra 2, you've probably learned about exponential functions, and factorials grow even faster than that. Okay, so let's do some problems. So I would advise you read the problems first, as always, and then pause the video and then watch me give the solution. So there are 9 competitors in a race. How many ways can they finish? So that's just 9 factorial, or 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 362,880. Now for factorials, you can also use your fundamental counting principle for this. So if you remember back in section 3.1, we talked about the fundamental counting principle, and we talked about how to multiply things together. So if you have 9 people running the race, how many ways can the first person finish? Well, that's 9. Now if the first person finishes, how many left is there away for the second person? 8, and then 7, and then 6, and then 5, and then 4, and then 3, and then 2, and 1. And the fundamental counting principle says to multiply these together. So notice that this is the same thing as the 9 factorial. We're just kind of simplifying it. All right, and how many different ways can the numbers 0 through 5 be ordered to make a 6-digit security code if none of the digits can be repeated? Well, the digits 0 through 5, there's 6 digits there, including 0, so that's 6 factorial. And very similarly, that's 6 times 5 times 4 times 3 times 2 times 1, which is 720. Okay, let's do the next one here. So the next one is we want to find the number of permutations of n distinct objects taken r at a time. So to find out how many ways we can do this, basically we have a group of n objects, and then we're taking r of them and permutating them. So to do this, we'll take n factorial, which is how many ways we can rearrange all of the objects, but we don't care about the ways that we can rearrange the objects we aren't selecting. Well, if we're selecting r objects and there's n objects total, we can represent the number of objects that we are not selecting by n minus r. And we divide n minus r factorial away because that divides out all the different ways that we are rearranging the objects that we are not selecting. So permutations, or NPR, is a very useful tool. For example, if you have something like a four-digit security code can be formed and no digit is repeated. Well, there's 10 digits, and we're permutating 4 because we're selecting 4 digits. And you can put this in your calculator. There should be an NPR button in your calculator under that PRB button, probably is where it's usually located, or you might have to look it up or just Google it, search it, and find where it is. But if you type in 10, then do NPR and then 4 is generally the, at least for Texas Instrument calculators, how to put it in. You should get the correct answer. So 10 factorial over 10 minus 4 factorial. We'll go old school here for a minute because the factorials are fun to mess with. So this is 10 factorial, and this is why they're fun to mess with. Because if you do this by hand, that's the top. 10 minus 4 is 6, so this is 6 factorial. And then you have a canceling fiesta, right? So really all we're doing is 10 times 9 times 8 and times, I just realized I forgot the times 7. I'm so silly. Yeah, times 7. Okay, so 10 times 8, or 10 times 9 times 8 times 7 is 5,040. And something that you should know is the fundamental economy principle may be easier for this one. So like if you consider yourself a 4-digit security code, there's 10 possibilities for the first digit and you can't repeat. So there's 9 and then 8 and then 7, and this is the exact same thing, right? So that's just something to keep in mind. Let's do the next one. So there's 40 competitors in a race. We care about finishing first, second, and third. So that's 40p3, which is going to end up being, there's 40 possibilities for the first person, 39 for the second, and 38 for the third. So you could do 40p3 in your calculator, or you could do 40 times 39 times 38. Either way, that's 59,280. So that's permutations of selecting r objects from n objects. The last type of permutation is a distinguishable permutation. And distinguishable permutations occur when you have objects of the same type. So what we do is we start with n factorial. That's how many ways we can rearrange all the objects. And then we divide out n sub 1 factorial, n sub 2 factorial, all the way to n sub k factorial, depending on how many categories we have. So sometimes you have things of the same, objects of the same type, and if you rearrange them, it doesn't matter how it looks. For example, if I want to find out how many ways I can rearrange, let's say I have 2 red balls, a green ball, and a blue ball, and I'm going to find out how many ways I can rearrange these. Well, that's 4 factorial, which would be 24. But the thing is, I'm going to divide out 2 factorial for the red balls, and I don't really need to worry about the 1 factorial and the 1 factorial because it's 1. But my point is that if I switch a red ball with a red ball, like if I switch these two, does that look any different? And it doesn't. So really, this would only be 12 different permutations because I have 2 objects of the same type. And that's the kind of thing that we're talking about in this case. So once again, try to use this concept for the remainder problems on this page, and then I'll go over them. So the first one is a building contractor is planning to build a subdivision. We have 4 one-story houses, 3 two-story houses, and 2 split-level houses. So that's 9 houses total. There's 4 one-story, 3 2, 2 split-level, and you can use the fraction button in your calculator, which is very useful for this, and you can put multiple factorials in the same line, but I like to do this. Cancel, cancel, cancel. 3 2 is 6. 2 goes into 8 4 times. So really you only have to do 9 times 4 times 7 times 5, which is, what is that? 63, 1,260, I think. Sounds right. Okay. Let's keep going. So the next one is a professional decorator. 4 pictures, 2 statues, 6 flower arrangements. So that looks like 12 factorial. And then there's 4, 2, and 6, which would be 13,860. Okay. And I'll save you the grief of canceling everything again for this one, but again, you can just put that part in your calculator, but you should know how to eliminate factorials. It's useful to know because you may have to do it. For example, if you have something like 100 factorial over 98 factorial, if you put this in your calculator, it'll give you an overflow error, but really all this is 100 times 99. Because everything 98 and below is going to be canceled everything on top. So the answer is 9,900 is what this is. So that's something useful to be able to simplify factorials, because your calculator will not do everything. All right, how many different ways can we rearrange the letters in the word Mississippi? So very similar thing. Mississippi has 11 letters. There's 1 M, so I'm not going to write it, but there are 4 I's, there's 4 S's, and there's 2 P's. And you should get 34,650. And for the last one, I normally pick a name in the class that has a lot of repeating letters, but since this video is being made and I don't have someone to pick on, let's do a fun word like hippopotamus. Why not? So it looks like there's 12 letters in the word hippopotamus, and then there's 3 repeats of P and 2 repeats of O. And the answer to this one's 39,916,800. Try to write out all the ways, different ways you can rearrange the letters in the word hippopotamus. I think that's going to take you a little while. Okay, and those are distinguishable permutations. So the last type of rearrangement we're going to talk about is a combination. And a combination is when order does not matter. So because order does not matter, because order does not matter, you do not care about the arrangement of the objects you're selecting. Once you select them, you're done. So I'll write this in parentheses. Order does not matter. And this is denoted by NCR, or it's denoted by N over R in parentheses like this. So if in a combination, we still figure out the total arrangement of all the objects, which is N factorial, and we still don't care about the objects that we're not selecting. So we still divide out N minus R factorial. But we also don't care about the rearrangement of objects that we are selecting. So we have this additional R factorial in the denominator. So let's talk about this. It says a state's Department of Transportation plans to develop a new section of interstate highway and receives 20 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 20 bidding companies? So there's 20 people we're selecting from, and we're choosing 4 of them. And this is a combination because I'm selecting 4 of the 20, and I don't care the order that I get those for. So this is just 20c4, which would be 20 factorial over 20 minus 4 factorial, 4 factorial. And you might be thinking, is there a button for this in your calculator? Yes, it's NCR. You'll probably find it under the PRB menu again, but that is the button in the calculator. And if you did this, you get 4,845. The last one, there's 10 people running for a spot on city council. There are 3 spots open on the council, and how many ways can the 3 people be selected? So that's 10 choose 3, which is 120. All right. So in terms of counting, there is basically, we talked about in section 1, the fundamental counting principle, which is m times n. There's a basic permutation, which is just rearranging n number of objects, so that's just n factorial. There is permutation, there's a permutation of npr, so r objects from n. So that's going to be n factorial over n minus r quantity factorial. There's distinguishable permutations, so distinguishable permutations, which is the n factorial over n sub 1 factorial, n sub 2 factorial, all the way to n sub k factorial. And then there's the combination, which is n factorial over n minus r factorial, but then we add the r factorial in the bottom. I shouldn't use the word add, it's really multiply, but you know, it's in the bottom. Okay, so those are the 4 basic counting principles that you should know about. And with these counting principles, you can also find probabilities. So for example, let's do a few probability problems. It says a student advisory board consists of 17 members. 3 members will be selected to serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve any of the positions. What is the probability of selecting at random 3 members that hold each position? So you have to think to yourself, does order matter here? And I always like to get the denominator first. So the denominator is how many total ways can we select 3 people as the chair, secretary, and webmaster? And since these are different positions, if I select the same 3 people, the order matters, right? Because if I select, let's say we have John, Ricky, and Sue, if John's the board chair, Sue is the secretary, and Ricky's the webmaster, I can select those same 3 people but switch around their positions, and that's a total different permutation. So it's a permutation. So in the bottom we have 17 because there's 17 total people and there's 3 positions, so P3. And how many of those positions has the correct position? How many correct positions are there? Well, there's only one where each of them are in the position that they are in. So that's 1 over 4,080. Which is 0.002. Okay, the next one. Find the probability of being dealt 5 diamonds from a standard deck of playing cards. So again, always think of the denominator first. So how many ways can I be selected 5 cards from a deck of cards? Well, remember, there's 52 cards in a deck. And since they're in my hand, the order doesn't matter. So this is a combination. So out of the 52 cards in a deck, I'm choosing 5 of them. And then in the numerator is fulfilling the event. Well, the event is getting 5 diamonds. How many ways can I get 5 diamonds? Well, there's 13 diamonds in a deck, and I'm choosing 5 of those. So we have 1,287 for the top, and we're going to divide that by 259, or actually 2,598,960, and the answer is 0.0005. Okay. Next one. A food manufacturer is analyzing a sample of 200 kernels for the presence of a toxin. In this sample, 3 kernels have dangerously high levels of the toxin. If 4 kernels are randomly selected from the sample, what is the probability that exactly 1 kernel contains a dangerous high level of the toxin? So again, may look complicated, but just think about it. What is the denominator? So where it says we have 200 corn kernels, that's our total, like our 52 cars in the previous problem. And we are selecting 4 kernels. So the total number of ways this can happen is 200 choose 4. Now, what is the probability that exactly 1 kernel contains a dangerous high level of the toxin is what we're trying to find. Well, how many do contain a dangerous high level of the toxin? Well, there's 3 kernels that contain a dangerous high level of toxin. So out of the 3, we're choosing one of them. Out of the 3 dangerous kernels, we're choosing one of them, times how many do not contain a dangerous high level of the toxin. Well, there's 197 because 3 plus 197 is the 200, right? And we're choosing 3 of those that make up all 4. So look at this pattern here. In the bottom, we have 200 choose 4 because out of the 200, we're choosing 4 of the kernels. Then 3 are dangerous. That means 197 are not dangerous. So notice how 3 plus 197 is 200. And then out of the 1 dangerous ones, we're choosing, and of the 3 non-dangerous ones, we're choosing. And 1 plus 3 is 4. So you have to remember you're choosing both the dangerous and you're choosing not dangerous ones. You have to include those in your count. And when you do this, you get 0.0582. The employee warehouse problem at the bottom, the next problem, is also very similar to this. So let's do this one as well. It says, a warehouse employs 24 workers on the first shift and 17 on the second shift. 8 workers are chosen at random to be interviewed about the work environment. Find the probability of choosing all first shift workers. So the denominator of the is the total amount of workers, which is 41 because there's 24 workers and 17 on the first shift. So that's 41. You're choosing 8. Now, if I'm choosing all first shift workers, that means of the 24, I'm choosing 8. And that's it. That's 0.0077. What about all second shift workers? Very similar. Denominators, 41 choose 8. But it's 17 choose 8 for the numerator because now we're only talking about the second shift. So that's 0.0003. And then we're going to do 6 first shift workers. So this one's a little more complicated. We still have 41 choose 8 on the bottom. But if there's 6 first shift workers, that means of the 24, I'm choosing 6. But that means of the 17, I'm choosing 2. Because if there's 6 first shift, I still have to choose 8 in the end. So the other 2 have to come from the second shift. So I have to multiply 17 choose 2 to get the remainder of workers from the second shift. So that's 0.1916. And then the last one is going to be, again, 41 choose 8. But now there's 4 second shift workers. So that's 24 choose 4. Times 17 choose 4, and the answer to this one is 0.2647. Yeah. So the probability ones I'm not as concerned about on, but you should definitely be able to evaluate and find and know the difference between permutations, distinguishable permutations, selecting permutations or objects from a group, and combinations as well. You should definitely be able to know when to use which counting process. All right. And that wraps up chapter 3 for probability.